In this problem, we determine the reaction order of reaction first, and then there's a series of calculations associated with the integrated rate law. Initially, the experiment was done, and we collected time versus concentration data, and plots were constructed of 1 over the concentration versus time, and ln of the concentration versus time. So we see from the data that our linear plot has been obtained on the plot that is 1 over the concentration versus time. That indicates that this is second order. With respect to NO, as we look to the form of the equation, 1 over AT is equal to positive KT plus 1 over A0. And this is our linear plot for second order, and our slope of this equation would be equal to K. Okay, this is in the form of y is equal to mx plus b. So our y-intercept is 1 over A0, this point here. Concentration at time 0, or our initial concentration. We know that this reaction is not zero order because the plot of the concentration versus time is not linear. So this is not 0th order. And it's not first order since the plot of ln of the concentration versus time is not linear. So the reaction is second order with respect to NO. We can write our rate law that the reaction rate is going to be equal to some rate constant K times the concentration of NO2 raised to the second power. Alright, so the question now becomes is how can you determine the rate constant? We've talked about that. When the equation is in the form of y is equal to mx plus b, m corresponds to our slope, which is k. So k is equal to the slope. It's equal to our rise over our run. So we could pick points on the curve corresponding to data points. This would be our rise over the run. So we would measure delta y over delta x, and that would correspond numerically to our value of k. Let's suppose we did this, and if we did this, we would find that our value of k would be equal to 0.54, the units being liters per mole dot second. So now we have our integrated rate law. We know it's second order, and we know the value of k. So we can calculate our concentration at any given time. Here, let's calculate the concentration at 20 minutes. So our second order integrated rate law is 1 over A of t minus 1 over A0 is going to equal positive kt. We're going to solve for A of t. So initially we'll solve for 1 over A of t. That's going to be equal to kt plus 1 over A0. We substitute in our values. K is given, or we determined what K is, 0.54 liters per mole dot second. Our time is 20 minutes. And we're going to have to use a conversion factor so that our units work here. So we know that every minute is equivalent to 60 seconds. So our units of seconds cancel, our units of minutes cancel, and we're left with liters per mole, which would correspond to the inverse of a concentration. Now we're going to add reciprocal of the initial concentration, which is 0.8 or 0.008, 0.00800. Units are moles per liter. So our value for 1 over A of T, let's see, this comes out to be 648, and this is 125, the units being liters per mole. So 1 over A of T is equal to this value. So it's going to equal 773 units are liters per mole. So A of T is going to equal 773 liters per mole. To minus 1 power, we need to take the reciprocal of that, and that comes out to be 0.001294 moles per liter, which with 2 sig figs is equal to 1.3 times 10 to the minus 123 minus 3 moles per liter. Okay, the half-life of the reaction at a given initial concentration. Note this is a second order reaction, and T1/2 for second order is not a constant value. But rather, it depends on the initial concentration. So T1/2 is equal to the reciprocal value of K times A naught. K is 0.54. And A0 is 6.00 times 10 to the minus 3, and this equals 308.64 seconds. With 2 sig figs can be written as 3.1 times 10 to the second seconds. We're going to calculate the half-life at a different initial concentration, okay, primarily to reinforce this fact here. The half-life for a first order reaction is constant, but for second and for 0th order they differ. They would depend on the initial concentration. So we do the same calculation but with a different initial concentration. And in this case we'd get 617 seconds, or 6.2 times 10 to the second seconds with 2 sig figs. Okay, the last question is how much time will it take for 25% of the NO2 to react? If 25% reacts, the amount remaining is going to be 75% of what we started with. So the amount at this time is 0.75 times our initial concentration, which is 0.75 times 8.00 times 10 to the minus 3. So A of T at this targeted temperature is going to be 6.00 times 10 to the minus 3 moles per liter. Alright, so our second order integrated rate law, 1 over AT minus 1 over A0 is equal to KT. We're going to solve for T. T is then going to be equal to 1 over AT minus 1 over A0, and that whole thing is over K. Okay, we can plug in our values. And when we calculate this out, our value is 77.16 units or seconds, and with 2 sig figs, our final answer is 77 seconds.